Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the short conference, Augmented Artificial Intelligence. Finally, there are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. In 1972, in the book Human Problem Solving wrote by Alan Newell and Herbert Simon. Thank you very much for your attention. There are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. We define augmented artificial intelligence, AAI, as the creation of artificial intelligence from the neuroscience of human intelligence, integrated with the mathematical laws of smart physical systems. The creator of the human brain conceived it as the integration of three main organs, or systems: neocortex, hypothalamus, and hippocampus. Human knowledge is supported by two types of models. Mental model: it is the abstraction or conception of what is perceived by individuals about a given issue or problem. Mental models are constructed with the knowledge, experiences, assumptions, perceptions, intuitions, informal inductions, deductions, and values of the individual. They are elementary models that are not exposed in public and therefore have a validity limited to the individual. They have their origin in the evolution of the human being, hominization, from the most primitive ancestors, Australopithecus, to the appearance of our species as we know it today, Homo sapiens. All human beings manage mental models, very quick to solve, and, in their absence, easily copy themselves from a more influential individual, and more recently, are implanted in human beings through the ochlocracy of mental models distributed by social networks. When intelligence works under this model, we will call it mental intelligence. Second, mathematical model is a scientific representation which make use of mathematical language to describe or to explain the portion of reality that is of particular interest to an individual. It is the result of the research carried out by certain humans. The mathematical models are growing as analytical tools that provide greater processing speed to the investigation. For its understanding requires formal training in mathematics and in the science being modeled. These models increase the intelligence of human beings, creating large differences, chasms, between them. When intelligence works under this model, we will call it mathematical intelligence. To evolve from mental intelligence to mathematical intelligence, the human being requires another type of intelligence that allows to perform the analyses to understand and discover the models that govern the universe. We will call this intelligence analytical creative intelligence. This intelligence can be considered as the highest level of human intelligence, since it is what allows to grow in the discovery of mathematical laws, and in general new knowledge, which is the engine of the scientific and technologic development of humanity. To create creative artificial intelligence, little progress has been made, and therefore, it seems that is distant the time when artificial intelligences be capable of creating knowledge that can be used to develop creative cognitive robots as part of the I. Now we can explore where we are. And where are we going? Traditional AI has concentrated on developing mathematical models, which try to imitate the functioning of mental intelligence, based on the structure of functioning of the brain, to represent the mental models associated with the processes of intuition, perception, deduction, just like humans, without using formal mathematical models, using fundamentally data-driven models. This process has been successful in relation to advanced predictive analytics since machines are able to emulate and overcome, in many facets, the mental functioning of humans. For example, pattern identification is increasingly performed by robots with greater precision and greater speed. This success is magnified when AI is given the ability to chain sequential recognition of multiple general patterns to a specific individual pattern, for example, identifying a specific person. Augmented artificial intelligence will be the new era of artificial intelligence will be based on the study of the operation of the neocortex and the real-time communication between algorithms, or cognitive robots, to build networks of mathematical models that allow organizations to act in a similar way to the human brain, making intensive use of distributed processing. The artificial hypothalamus corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence to los organizations, or parts therein. Storage structures and processes from the decision-making that must be faced permanently. The artificial hippocampus is based on the mathematical synthesis of the information generated by algorithms and problem-solving processes, to use it in new runs of these algorithms to speed up the problem solution in real time. When formal mathematical models of real systems are known, the inability to use them, in human everyday life, is directly related to the very low speed of mathematical calculation that humans have, which does not allow the scientist to solve in real time the mathematical problem associated with the knowledge that he has. For robots, computer technology has overcome this inability, allowing them to solve in real time increasingly complex real problems. Only when humans will be able to bring the mathematical calculation power to the human brain, we can use the known mathematical models in human everyday life. However, organizations can already build their own artificial hypothalamus, using existing computational power. The central axis of this possibility lies in developing a standardized language between algorithms, that allows to build an artificial hypothalamus so that multiple algorithms, representing agents, interact autonomously in real time, taking advantage of the information stored in an artificial hippocampus. This could be called Mathematical Programming 4.0. Based on distributed parallel mathematics, and not on the traditional concepts of monolithic and sequential electronic calculus. Human intelligence and sparse artificial intelligence. Jeff Hawkins is an advanced researcher in the application of neuroscience to the development of artificial intelligence. As a result of his studies at Numenta Incorporated, Hawkins proposes the sparse artificial intelligence model, whose main characteristics are. Hawkins proposes the sparse artificial intelligence model, composed of columns and layers that performs robust object learning and recognition. Columns integrate their changing inputs over time to learn complete models of observed objects. Lateral connections across columns allow the network to more rapidly infer objects, based on the partial knowledge of adjacent columns. Because columns integrate input over time and space, the network learns models of complex objects, that extend well beyond the receptive field of individual cells. The Hawkins network model introduces a new feature in cortical columns, that proposes that a representation of location calculated within the subgranular layers of each column. The representation of location is relative to the object being sensed. Pairing sensory features with locations is a requirement for modeling objects and therefore must occur somewhere in the neocortex. Hawkins proposes it occurs in every column in every region. The network model contains 2 layers and 1 or more columns. Simulations show that small single-column networks can learn to recognize hundreds of complex multidimensional objects. Given the ubiquity of columnar and laminar connectivity patterns, the columns and regions have more powerful recognition and modeling capabilities than previously assumed. In summary, the modeling of the structure of neocortical regions is organized into columns and layers. Connections between layers run mostly perpendicular to the surface, suggesting a columnar functional organization. Some layers have long-range lateral connections, suggesting interactions between columns. Similar patterns of connectivity exist in all regions, but their exact role remain a mystery. All regions have a motor output. Hawkins' work gives rise to the HTM neuron, that is intended to emulate the overall structural and functionality of the human neocortex. The main properties of HTM is hierarchical structure, sparsity and modularity. Another important contribution of Hawkins is related to the multiple brain models of the same object working cooperatively. For example, to recognize an object, 5 models of that object can intervene, each of them generated by one of the senses that the human being enjoys. Complete knowledge occurs when the knowledge generated by all models in all layers are integrated. Hawkins proposes the concept of regions, groups of cells organized hierarchically, interconnected, but with a low density of links, sparse. Interested people can consult the work A Thousand Brains on YouTube. High-speed parallel computing and mathematical revolutions are the pillars of the evolution of advanced analytics. Algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world. Muhammad ibn Musa al-Khwarizmi, mathematician and Arab astronomer, introduced European mathematicians into the Indo-Arabic numerals and in the fundamental principles of algebra. René Descartes was a French mathematician, physicist and philosopher, considered the father of the algebraic and differential geometry. Sir Isaac Newton was an English mathematician, physicist, astronomer, and theologian, widely recognized as one of the greatest and most influential scientists of all time. He was a key figure in the philosophical revolution known as the Enlightenment. Newton made seminal contributions to optics, and shares credit with German mathematician Gottfried Wilhelm Leibniz for developing infinitesimal calculus. Joseph Louis Lagrange was an Italian mathematician and astronomer, later naturalized French. In mathematical optimization, the method of Lagrange multipliers is a strategy for finding the local maxima and minima of a function subject to equality constraints. Using the implicit function theorem, the seminal Lagrange idea is to convert a constrained problem into a form such that the theory of an unconstrained problem can still be applied. George Bernard Dantzig was an American mathematical scientist who made contributions to industrial engineering, operations research, computer science, economics, and statistics. Dantzig is known for his development of the simplex algorithm for solving linear programming problems, and for his other work with linear programming. In statistics, Dantzig solved two open problems in statistical theory. The primal simplex algorithm can be considered the starting point of applied mathematical programming, and the birth of computer-oriented mathematics. Mathematical programming is characterized by having an objective function as decision criteria, and a mathematical model, based on a set of constraints that represent the industrial's process, and the business rules. In 1962, the Dutch mathematician Jacques Benders publishes his theory of partition that is a transcendental step, not the first, in parallel computing, aimed at solving complex mathematical problems, dividing them into more elementary subproblems. The importance of Benders' theory, which followed the work of Dantzig-Wolff, is that it resulted in parallel optimization, based on the theory of duality, which today is the key to a dynamic language for cognitive robots, based mathematical programming algorithms to build artificial hypothalamuses. Based on the concepts of partitioning and decomposition, it is possible to decouple a system, to obtain vertical structures partially similar like of the human neocortex. In 1983, Tony Van Roy created the cross-decomposition approach, to solving large-scale optimization problems, based on partitioning and decomposition techniques, and mixing different types of methodologies, such as Lagrangian relaxation and Benders' theory. From the point of view of multi-layer structures, cross-decomposition gives rise to the exchange of information between multiple layers, of different columns, such as the real structure of the human neocortex. All the developments, in mathematics applied to solving real-life problems, converge to parallel processing and the large-scale mathematical programming. Artificial brains are backed by the technological capacity of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, integrated by supercomputers of bits, and by the birth of quantum computers, which are the beginning of a new era. The current state of the computer technologies involves the integration of edge computing and cloud computing to implement systems with multiple highly complex mathematical models that can be run in parallel. This allows us to talk about autonomous real-time distributed optimization. Neocortical regions and large-scale mathematical structures. In optimization models, it is common to use a matrix that relates columns with variables, and equations with rows. structurally similar to that of the human cortex. Depending on its complexity, the ways to divide a system may be non-numerable. The diagram shows a two-level structure. This diagram shows a three-level structure. When comparing the human cortical structures with cortical structures of animals, it has been found that the complexity, number of layers and columns, increases with the intelligence of the living being. This is consistent with the fact that, the greater the complexity in the structure of optimization algorithms, speed off the solution time, and produce greater the understanding of the problem being faced. In a multi-level mathematical model structure, the different levels can be characterized by the type of processing they perform. Large-scale methodologies generates three processing areas. Holistic, that coordinate all processes and solves the problem. Communicative, all intermediate layers responsible for adjusting the information that is transferred between the uppers layers and lowers layers. Sensitive, intensive in generating basic information that produces the data that is processed in the upper layers. In dynamic systems it should be related with time dimension. When simple problem division methodologies are applied, verticalized structures are obtained, that ignore the transfer of horizontal communication. More complex methodologies, such as cross-decomposition, generate cross-structures like the real structures of neocortex. Everything indicates that the structure, and joint functioning of the neocortex and hypothalamus, is like the structure of the most advanced optimization algorithms. This strong relationship can serve to deepen the knowledge of the two disciplines, artificial intelligence and mathematical programming. Artificial hypothalamus structure. Traditionally, low mathematical complexity modeling is based on a top-down approach. In this approach, the process of disaggregation of the whole is carried out by empirical rules of proportionality, of low representativeness. Parallel computing has opened the way for bottom-up modeling, in which the system is built from atoms, whose operation is scientifically integrated. The advantages of this approach are: having more layers of modeling, the atom's representation is more detailed. Having more atoms, the cells of the last layer, the mathematical problem is smaller, then the amount of resources required to solve the problem are less. Top-down implies a monolithic vision, based on sequential synchronous mathematics. Bottom-up a parallel vision, based on parallel asynchronous mathematics, oriented to large-scale optimization methodologies. The solution of an optimization problem using large-scale methodologies is based on partitioning the problem into two sub-problems that must be solved in coordination. It can be said that there are two basic methodologies that bring together majority of applications: Bender's partition theory, BT, and Lagrangian relaxation, LR. They can be considered complementary. In BT, the partition is performed according to the variable's type. It is a primal method that works on primal feasible zone. In LR, the partition is performed according to the constraints type. It is a dual method that works on dual feasible zone. The methodologies of large scale are not limited to being mathematical tricks to solve the problem. They have a full techno-economic interpretation that helps to understand the inner workings of the systems. For example, in the case of BT applied to a multi-business company, the information that each subproblem generates corresponds to parts de Cobb-Douglas production functions, defined based on convex hull represented by cutting planes. The large-scale optimization methodologies define an exchange of information between problems, based on the duality theory. If we associate each subproblem with a robot, it can be said that Bender's created a language to communicate mathematically cognitive robots, algorithms, working cooperatively to achieve a common goal. This is the same goal of the human hypothalamus. Artificial neural networks can also be associated to networks of algorithms, representing agents, of an organization, or system. Each of these agents could be associated with a superneuron, that performs a much more complex transformation than that of a conventional neuron. On the other hand, the structure and communications of the artificial superneurons net, ASN, are determined exactly by mathematics. In addition to the network, communications between neurons, centralized communications between mathematical problems or algorithms. Based on these concepts, Hi has developed the artificial brain framework, composed of a neocortex, a hypothalamus, and a hippocampus. Like the human hypothalamus, the artificial one is responsible for guaranteeing the balanced development of a company, coordinating in real time, algorithms that act autonomously and process information in a distributed way. An artificial hypothalamus can be seen as the intelligent and autonomous coordination of algorithms, or as coordination of robots. The concept of artificial hypothalamus can be applied to solve real-life problems from multiple points of view. In the diagram, the artificial hypothalamus coordinates models corresponding to the multiple problems faced by a company, organized from the point of view of its administrative functions. Another point of view is the spatial distribution of the problem. In this case, an artificial hypothalamus is presented for an agro-industrial company that has multiple facilities, farms, concentrated food factory, meat products factory, and stores in the food market. Asynchronous parallel optimization for artificial enterprise hypothalamus is viable thanks to supercomputers and super algorithms that allow, at reasonable costs, to solve increasingly complex problems in increasingly shorter solution times. Partitioning and the decomposition of a system can occur in multiple ways, without there being a mathematical reason to select one as the best. The diagram presents a system that can be sorted hierarchically by three alternative criteria: business, regions, and functions. Alternatively, it is possible to choose another hierarchy: regions, business, and functions. It is important to note that in both cases it is met. The last layer, the sensory one, is the same since it corresponds to the atoms of the system. These could not change according to the point of view. The upper layer, the coordinators, is partially the same, since in each of them, the information corresponding to the alternative point of view is missing. Hierarchies can be associated with multiples views of the same system, as proposed by Jeff Hawkins. Considering the vision of large-scale optimization as multiple points of view, Hi developed the Bender's multi-decomposition methodology. To solve complex mathematical optimization problems associated to large enterprises, the optimization problem may be decomposed using different point of views. In many cases there is no obvious hierarchical order, first business after regions and finally functions? Or first regions then business and finally functions? Or the algebraic formulation depends on the hierarchical order, but the optimal solution must be the same regardless of the point of view. The advantage multi-decomposition arises when subproblems are solved based on an asynchronous parallel approach. In this case, each time a problem is solved, a cutting plane is included in the coordinator problem, in such a way that the number of mathematical elements included depends on the optimization process, the number of cores used, the numbers of vision of the system, and the structure of each of the subproblems. Then, it is possible to modify the standard large-scale methodologies to include mathematical elements from the different points of view, and they could speed off the solution process, and to have a better vision of the system. To the extent that a more complex structure is elaborated, the artificial hypothalamus becomes a supernet of artificial superneural nets. Real-time smart and autonomous communication between robots. A cognitive robot is an artificial intelligence algorithm that can have a holistic view of a problem and solve it using high-complexity mathematical modeling, based on distributed multivision parallel asynchronous mathematics. Examples of this type of intelligence are the algorithms capable of optimally planning and operating a supply chain or a hospital or factory, planning the location of facilities in a smart city, managing fleets of vehicles, optimizing energy consumption, scheduling the staff of a plant, controlling the risk associated with the financial distribution of assets and liabilities of an organization. An artificial hypothalamus corresponds to a superalgorithm that coordinate multiple cognitive robots that operating simultaneously, autonomously, in real time, acting as the human hypothalamus, to achieve a common goal. The central part of an artificial hypothalamus is the formalization and the standardization of a math language between cognitive robots, to be used as the way to communicate multiples math algorithms. The core of this language is the duality theory, that support the mathematical programming algorithms, that may be developed using the concepts of large-scale optimization methodologies, to solve high complex math models based on the partition and the decomposition of the real-life complex systems. By joining all the concepts presented here, it is possible to define a language between robots, math problems, algorithms, or agents, based on an exchange protocol of information between the multiple types of problems, in which any pair of robots communicate by exchanging the information produced by each of them, which is synthesized in the value of the primal and the dual variables that they produce. If each robot is identified by the R index, in each conversation step K, the actions of each robot are inputs, dual and primal variables that our robot uses produced by other robots. All the data available until the begin of conversation step K is characterized as the historic knowledge database QK. Outputs, primal and dual variables that produce the robot R, it can be characterized as XKR, PKR. Transformation function FRQK, mathematical problem that the R robot solves to produce XKR, PKR, starting with QK. Mathematically this is XKR, PKR, equals FRQK. QK equals QK minus 1 union with XKR, PKR, Q0 equals. When our robot receives information QK, it processes it, generating information, XKR, PKR, and a conversation step K plus 1. The robots receive, or search, the inputs produced by other robots, and produce the outputs to be used for other robots. The information produced is added to the historical, and it is stored in the artificial hippocampus, an intelligent database on disk, or in RAM, which can be accessed in the next conversation of all robots. Then, based on large-scale optimization methodologies, communication between robots is synthesized in the transformation functions FRQK and in the storage of all the information produced, XKR, PKR, in an optimization knowledge database, QK, which can reside on RAM disk, offline, or on RAM memory, online. In a static problem, frontier conditions fixed, when the coordinator robot detects that has enough information to establish the optimal decision, it proceeds to close the conversation cycle, and terminates the optimization process. If the problem is dynamic, frontier conditions time-dependent, the robots will have a continuous conversation in order to keep the system as close as possible to the optimal decision path, which is not possible to obtain due to system uncertainty. This process, based on duality theory, is the support of artificial hypothalamus capable of processing the information required for Industry 4.0. Artificial hippocampus structure. The learning process of the human being is concretized in memory, which accumulates information, data already processed, to face each new situation, using the knowledge stored that has been made up to that moment. This knowledge is stored in the hippocampus where the data is organized according to its age. Like any physical element, its use affects its reliability, and that is why short memory, the one that stores the data of the last moments, begins to fail with age, until it is lost, while long-term memory can store very sharp data, but that require greater access time to locate them. In a very simplistic way, it could be said that the hippocampus stores information to support human decision-making, using two strategies. Guide the humans to achieve the goals that give you pleasure, well-being. Protect the human being from what he does not want, or should not, or cannot, succeed him, because of the consequences that may entail. For example, a basic artificial hippocampus can be constructed using Bender's partition theory, which can be interpreted as: the general problem is divided into two complementary subproblems, an experimenter, that makes decisions in real, or in simulated, environments, and that send the results to the higher level, and an information manager, that stores the results, sent as primal and dual variables. When it is required to make a real decision, or to perform an experiment, the information manager processes the stored data to determine two zones with respect to decisions, a desirable zone and a non-desirable, or utopian, zone. Mathematically, this is done by generating cutting planes and incorporating them as part of the information to be processed. The experimenter receives the information from the manager, makes decisions, and sends the results to the manager. The speed with which this loop is made can be that of an algorithm that does not stop until it finds the optimal solution, or that of a human who makes decisions step by step. The first non-optimal zone that contain values of the decision variables that must be discarded because they cannot be optimum. From a human point of view, it contains decisions that should not be taken because there are better. The second non-feasible zone that contains values of the decision variables that must be discarded because they cannot be feasible. From a human point of view, it contains decisions that cannot be taken because they are impossible. Decisions not included in the two zones determine the area of rationally desirable and possible decisions. As the learning process progresses, the convenient area is reduced in such a way that many decisions seem intuitive. If memory does not fail, the humans will remember in each new decision-making process the story, and their decisions will be faster and more successful, and they will learn from each decision made. Following the principles developed by Benders, it is possible to build an artificial hippocampus that remain active and useful beyond the duration of a run of a computer model. To do this, the cuts generated in each run must be stored in such a way as that they may be used later. This implies a coordination work, since it cannot be guaranteed that the information as it is produced can be reprocessed later. An artificial hippocampus stores cuts from one run to be used in the next, which will produce new cuts. Hai is researching in the creation of methodologies to generate new rules that fit the dynamic variation of the parameters that affect the models. Another alternative to generate knowledge that is stored in the artificial hippocampus is the generation of convex hulls associated with optimal solutions of the mathematical problems. The multidimensional grid that represent the convex hull can be incorporated into the integrated problems to accelerate the solution process. Depending on the specific problem, the convex hulls may be permanent, or they must be recalculated dynamically when the parameters of the mathematical models change. Convex hulls allow flexible approaches, as in the case of an energy transmission system, in which they can be associated to two different ways to solve the problem flow AC and DC flow. The production of convex hull of optimal points is a standalone process. Therefore they can be generated outside the optimization process. Algorithms swarm. If large-scale multi-level optimization methodologies, based partitioning and decomposition of systems, are applied to get the smallest atom of a dynamic stochastic, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms that work autonomously and permanently to achieve the goal proposed by the decision maker. This algorithm swarm approach is currently used in artificial intelligence to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and have no solid mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level sparse matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining team results. Finally, there are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. In 1972. In the book Human Problem Solving wrote by Alan Newell and Herbert Simon. Thank you very much for your attention. Galileo Galilei affirmed, mathematics is the language in which God has written the universe. Hai believes that mathematics may be the language with which God has written the human brain. Thank you for your attention.